Hello. In this notebook, we are going to see vision transformers and the frontier of computer vision. In 2020, a team of Google asked a bold question. What if you applied the transformer, originally built for text, directly to images? The result was the Vision Transformer or VIT, and it launched a revolution. This notebook builds VIT from scratch and shows you clip Dino Sam Swin Transformer and Connext. The models reshaping computer vision today. We are running on an NVIDIA A100 with 85 GB of GPU memory, so the code runs fast. In the setup, this is a standard setup. The key here is the hardware. An A100 with 85 GB of memory. That is what lets us load and run models like Dino and Connext in this notebook without running out of memory. Chapter 1, the attention mechanism. Before we build anything vision specific, we need the attention mechanism. It takes three inputs: query, key, and value. The query asks, what am I looking for? The key says, what do I contain? And the value says, what information will I provide? We compute dot product between queries and keys, scale to the square root of key dimensions to stabilize gradients, apply softmax to get probabilities, then multiply by values. Every row in the attention matrix sums to 1. It's a weighted average of the values. Next, we have multi-head attention. What the code does here is it implements multi-head attention, projects QKV into H head subspaces, runs attention in parallel, concatenates output, and projects back. Multi-head attention runs 8 independent attention operations in parallel. Each head uses a lower dimension projection. 8 dimensions each if we divide 64 by 8. The outputs are concatenated and projected back to 64 dimensions. Different heads learn different relationships. One might track horizontal edges, another vertical, another texture. The output shape is identical to the input and the module is perfectly composable. Next, we have visualize attention patterns. Each panel is one attention head's weight matrix. Rows are query positions, columns are key positions. Notice they all look different. Even on random input, each head develops a distinct pattern. Some concentrate attention on a specific position, others spread it broadly. While when trained on real images, these patterns become highly structured. Some heads track edges, others semantics. Moving ahead to chapter 2, Vision Transformer. In the patch embedding, what the code does here, it splits a 2 to 4 into 2 to 4 image into 14 into 14. 196 non-overlapping patches of 16 into 16 pixels each, then projects each flattened patch to a 768 dimensional embedding using a single conv2d layer. This is VIT's key insight. Treat an image like a sentence of patches. We divide the 2 to 4 pixel image into a 14 by 14 grid of 16 pixel patches. Each patch is a 16 into 16 into 3 blocks, 768 numbers when flattened. A single conv2d with kernel size 16 and stride 16 does the patching and projection into one efficient step. The output is 196 patch embedding each 768 dimensional, exactly like a sequence of word embedding. Visually, this is what patchification looks like. The red grid divides the image into 14 by 14 mosaic. Each square becomes one token in the transformer input. The right panel shows the first 16 patches zoomed in. Notice each patch is just a small tile of the image. The transformer's attention mechanism is responsible for learning how these tiles relate to each other. Next, we have transformer encoder block. One transformer encoder block has two sublayers. First, multi-head self-attention with pre-norm. We normalize before attention, not after. Second, A feed-forward MLP that expands the dimension by 4x to 3072 applies GLU activation, then projects back to 768. Both sublayers have residual connections. The input is added back to the output. With 197 tokens and 768 dimensions, one block has 7 million parameters. Complete VIT model. The full VIT base has 86 million parameters. The CLS token is a learnable vector prepended to the 196 patch tokens, giving 197 total, and its output after 12 transformer layers is used for classification. Positional embeddings are also learnable and give the model a sense of where each patch sits spatially. The final head is a simple linear layer mapping 768 dimensions to 1000 ImageNet classes. Moving to variant stable, VIT comes in 5 sizes. Tiny has 5.7 million parameter, small has 22 million, base has 86 million, which we just built, large has 304 million, and huge has 632 million parameters. The pattern, doubling the hidden dimension, roughly quadruples the parameters. VITB and above achieve competitive accuracy on ImageNet when pre-trained on large data sets like ImageNet 21K. CLIP, Vision Language Pre-training. CLIP, zero-shot classification. In the code, we have attempted to load CLIP. Since it is not installed, fallbacks to a detailed code example showing how to use it. CLIP, contrastive language image pre-training, trains two encoders jointly, a vision encoder and a text encoder. They trained on 400 million image text pairs scraped from the internet, pushed to produce similar embeddings for matching pairs and different embeddings for non-matching ones. The result is remarkable. To classify an image into any category, you just encode text like a photo of a dog and a photo of a cat and find which text embedding is closest to the image embedding. No task-specific training needed. This is a zero-shot transfer. Next, we have Dino V2, self-supervised visual feature. Dino V2 is a self-supervised VIT trained on 142 million images with no labels whatsoever. It uses knowledge distillation between a teacher and a student network with different crops of the same image. The output is two types of features. The CLS token gives a single 384 dimensional vector summarizing the whole image. Great for retrieval and classification. The 256 patch tokens give dense per patch features, great for segmentation and depth estimation. These features are often better than supervised models. Dino V2 model variants. Dino V2 comes in 4 sizes up to 1.1 billion parameters. Crucially, none of these required a single human annotation during training. The giant model achieves 86.5% ImageNet top 1 accuracy with a linear prop, a simple linear classifier on frozen features, surpassing many supervised models. Next, we have segment anything model, SAM. SAM is Meta's universal segmentation model. It separates the heavy lifting. The image encoder, a 632 million parameter VITH, runs once and produces a 64 by 64 embedding grid. Then for each prompt, a point, a box, or a rough mask, the lightweight prompt encoder and mask decoder run quickly to generate up to 3 candidate masks with quality scores. This design lets SAM be interactive. You encode the image once and respond to user click in real time. SAM usage example. Using SAM is straightforward. Load the model, create a predictor, and set an image. This triggers the expensive VITH encoding, then called predict with a point or box. You get three masks back ranked by quality score. The automatic mode can segment every object into an image without any prompts at all. SAM was trained on 11 million images and 1 billion masks, the largest segmentation dataset ever assembled. Part 6, we have hybrid architectures. Convenext asks, what if we modernized a classic REST-net using every lesson learned from transformers? The changes were systematic. Replace the 7 by 7 stem with a 4 by 4 strided patch. Use deep by 7 by 7 convolutions like transformers. Use large repetitive fields. Switch from batch norm to layer norm. Replace ReLU with GLU. Reduce activation and normalization layers. The result matches or beats Swin transformer on ImageNet with 28 million parameters, and it's a pure CNN, no attention needed. Next, we have Swin transformer. The Swin transformer addresses VIT's quadratic complexity. Standard VIT computes attention between all 196 patches. 196 squared operations. Swin restricts attention to local windows of 7 by 7 patches, then shifts the windows by half a stride in the next layer to create cross-window connections. This reduces complexity from quadratic to linear in image size, making it practical for high-resolution images and dense prediction tasks like detection and segmentation. Next, we have model selection guide in comparison. The notebook ends with a practical guide. Which model for which task? Based on scenario, the recommended models, and why. For classification on small data sets, use RESTNet with fine-tuning. For medium data sets, efficient net. B4. For large dataset, Convenext L or SwinL. For segmentation, SAM. For universal feature extraction that works across tasks, Dino V2 is the current best choice. Pre-trained model comparison table. This table captures the state of computer vision models. Dino V2B reaches 84.5% with a linear probe on frozen features, meaning a simple linear classifier on top of the pre-trained backbone with no fine-tuning. That is extraordinary for a self-supervised model. ConvNext and Swin are neck and neck at 82 to 83%. VITL tops the supervised model at 85.2%, but needs 307 million parameters to get there. Quick start code. The final cell is cheat sheet. 5 ready to use patterns. 1 load VITB from Torch Vision and swap the head. 2 is extract feature extraction with Dino V2. 3 is zero shot with clip. 4 is segment with a point prompt using SAM. 5 is fine-tune convnext for a custom dataset. These snippets are copy-paste ready. To summarize, VIT proved that images can be treated as sequences of patches and processed by transformers. Clip connected vision and language, enabling zero-shot recognition. Dino V2 showed that self-supervised learning at scale produces universal features better than many supervised models. SAM democratized segmentation with a promptable zero-shot interface, and ConvNext and Swin showed that the classic CNN and the transformer are not enemies. They both benefit from each other's ideas. Computer vision is in the middle of its most exciting era. Thank you for being there in the video.